I assume you've seen little gadgets like this, haven't you,
Yeah,
AJ?
they're little clocks.
Little clocks with things go flashing on and off. Well, it's not working, obviously, at the moment because the two wires coming out from the back end end up like this.
There's no battery.
Yeah, what we need is a battery. But we're not going to go to the store and buy one. We're going to make one of our own out of potatoes.
Potatoes?
Yeah. Back in the refrigerator are a couple of potatoes. Go get them.
Okay.
You see these two little cup-like things? Mm-hmm. You can see what they're for. Put the potatoes in them. Okay. Take one of these little electrodes and plunge it into the potato there. And take the other one and plunge it in and put the other potato. Nothing happening?
No, nothing.
That's because we don't have the potatoes connected. Here are two more electrodes with a little piece of wire like that. So I want you to, this one you put a copper electrode in, that one you put a zinc. So take these two and reverse it.
Okay.
At a little distance from the first one, like put them right on the top.
Okay. Oops.
That's copper and copper. Okay, there's zinc.
Zinc. There we go.
Clock running?
Yeah, it is. That's neat.
So that's a neat little thing you can put on your desk when people wonder, potato clock? Doesn't make sense, does it? Let me explain why. The important thing is not the potatoes, but these two little electrodes. I'll disconnect it. Okay. One is copper, as I mentioned, and the other is zinc. Yeah. And when you put them into a solution that has any kind of chemical reaction at all of the right type, electrodes are taken from the zinc, sent through the wires over to the copper. And that's what's running the clock.
Oh.
So this would run on soft drinks. You can try all kinds of stuff. Beets, beer, anything that'll fit into these. You can put the two electrodes in like that, and the clock should start again, right?
Yeah, there it is.
Yeah. Now, you don't need potatoes. You can use all kinds of other things, too, to make everyday sort of batteries. Over at the sink is a, see that beaker over there? Take it over and get it filled with water, and underneath the sink is some bleach. Bring that over, and I'll get some salt. Okay, here comes our battery.
Get some bleach.
So the important ingredients this time are the salt, water, and you recognize what these are, by the way.
Yeah, copper and zinc.
The copper and zinc. This is galvanized iron that you can buy in a hardware store. And those little crystals on the top tell you it's been covered with zinc. So, put those in the water. And we'll put these two stirring rods in there to make sure that they don't touch, it holds them apart.
Oh, yeah.
Okay, now, here is a motor. See it on the back there? Yeah. And I've got a spiral on the front of it so that when the motor turns, we can see it. And here come the two wires from the motor. So you connect that up to the two electrodes.
There we go.
Okay, now pour in some salt.
Okay.
I'll stir. Okay, that should be more than enough. We have a super saturated salt solution. See if we can give this a little start. Okay, now add just a little bit of bleach to start, and let's see what happens. That's enough.
Okay.
There we go.
Holy!
Okay, now why is it working? What is the principle kind of all battery?
The chemical reaction is sending a current from the zinc over down to the motor and then back up to the copper.
Right. And you can put together dissimilar metals and various combinations of everyday stuff. And you've just done what?
Oh, yeah.
Made one out of?
Potato kind of.
Potato?
And salt butter.
Right. Darren, here's a sort of a simple little problem that's a lot of fun to play on your friends, because unless they know the secret, they'll find it impossible. And once you know the secret, you'll realize, I think, a sort of important point on how to look at problems. Here, take the pen.
Okay.
What I'd like you to do is to connect those 9 dots with 4 straight lines without taking the pen off the paper.
All right.
1, 2, 3, 4. Missing 2. Okay. Now, the secret to the whole problem is to understand the problem in the first place.
Okay.
Remember when I said I want you to connect the 9 dots with 4 straight lines?
Yeah.
I didn't say how long the lines were going to be. And you automatically, when you started to draw the lines, you didn't go outside the dots at all.
Yeah, I figured that it automatically that it was inside the lines.
Yeah, and it doesn't have to be. So I'll start you this time, and I think you'll be able to finish it.
Okay.
I'll go like that.
Oh, okay.
Now you go ahead. That's 1. Keep going. 2, 3, 4. Very good.
Yeah.
So anyway, I said this sort of made an important point, and the important point is, whenever you are confronted by a problem, even in school or a test or a scientific problem, make sure you define the problem very clearly in your own mind and don't bring extra things to it that stand in the way of solving the problem. Now, you remember how to do this now?
Yeah, so I can just make sure that I don't think that it's always within the lines, that there's extra possibility.
Very good. Try that on your friends. I think you'll be able to catch them.
Sure, okay.
You're flying with a scientific crew on a dangerous mission to fly through one of the most powerful storms, a hurricane, to record the information that will help forecasters predict where and when the storm will hit land. Like all hurricanes, this one was born days earlier in the tropical waters around the equator. As the warm, moisture-filled air rises, the rotation of the Earth causes it to spin. As the winds increase and pick up more moisture, the cycle can build up into a hurricane. The first hint of a newborn hurricane usually comes from weather satellites or from ships in the vicinity of the storm. While most hurricanes travel the same general path, some go much further inland than others. The National Hurricane Center tracks the storm as it heads eastward. If it looks like it's headed for land, the hurricane watchers track it from the air. They ride through the strong winds circling near the center. The highest winds in this storm measure 230 kilometers or 143 miles per hour. They also measure the wind speed at various other areas in the widespread storm. With this information, scientists back at the Hurricane Center can more accurately predict the storm's path and give ample warning for people to protect their property and leave the area where the hurricane will probably hit the coast. When it finally does sweep on land, the people are prepared. This hurricane pushed water 4.5 meters or 15 feet higher than the usual high tide. As is often the case, the damage done by water was more severe than that caused by wind. A few hours later, the wind died down as the eye of the hurricane came ashore. As it passed, the other half of the hurricane swept in from the sea. Once over land, the storm begins to lose energy as it no longer has a supply of warm, moist air to build on. The friction of the wind wreaks havoc on the land, but weakens the storm even more. The hurricane could end up as a strong tropical storm, which eventually dissipates, or turn back out to sea and regain strength, and possibly head back inland, further up the coast. Scientists are gradually adding more information on how the many variables help generate and determine the direction of nature's most powerful storm, the hurricane. How you doing, Jason?
Pretty good.
Ah, I see Sears Tower. Oh, you're flying...
In Chicago.
In Chicago.
Yeah.
Well, can you sort of straighten it out a little bit? Because I'd like to know what you found out about the controls.
Okay, I'll turn this around here a little bit.
Okay, yeah, you're doing very well. How fast are you going?
Let's see, I'm going about 80 RPM.
That's the first dial on the left on the upper side there, okay? Yeah. Okay, and then the next one?
That's my horizon.
Okay, your nose is a little high above it at the moment. Right?
A little bit, not too much though.
Next one, I see your altitude.
Yeah, I'm at about 1,800 now.
Above sea level.
Yeah.
Right? Okay. Then the next one over there is is a radio-controlled sort of compass-like thing, which I think you can probably
I haven't tried that one
You
yet.
don't have to. Oh, there's the Sears Tower. Oh, you're really flying around there. Oh, and look at the one on the lower left. That's your wings, right?
Yeah, that's my wing tilt.
Okay, so now you're sort of straightening out. Now your right wing is down. And now you're going to straighten it up, I hope.
Yeah, I'm going to give it.
You see that Sears Tower at the top there. You're going to try to avoid that, are you, I hope?
Well, I'm going to try to get near it.
You're going to get near it, or you're going to buzz it?
Yeah.
All right. Well, actually, Jason, what you've been doing is a computer program that is very, very complicated in that the computer designer actually took in the characteristics of a small plane and built them into a program so that you working the joystick and looking at the controls can actually get the feel of what it's like to fly a small little airplane like that.
It isn't easy. Ooh.
It isn't easy. You know, it's a fairly complicated sort of machine and a very complicated sort of program. Now, you've used the sort of the beginner's setup, but actually when you look at the instruction book, you can set it up for a crosswind. You don't have any wind blowing at all, you see, so you don't have to worry about that. You could set it up for a couple of layers of clouds so that you have to use some of these instruments as you fly through them.
Wow.
You can also fly several different airports so that you could practice that. And the big trick is, of course, landing. Now, can you, you haven't crashed yet? You're now, what, 3,000 feet? You took off at 600 feet, right?
Yeah, I could shut off my engines.
Well, you could shut off the engine, too. You'd use the controls over here. Off goes the engine.
There I go. It's that little strip down there on the bottom, right on the right hand.
Yeah. You're down now at, here's crash coming up. You got 1,000 feet to go and you're going to crash. There's the ground coming up at you.
Oh, boy.
Yeah. Here you got about 200 feet, 100 feet.
Oh.
Crash. There.
Oh.
So the point is that you can't get into trouble because obviously, you know, what'll happen is the thing will automatically start over and you're ready to try again.
All right.
So there you are on the runway. So
okay,
crank up the engine and take off and away you go. Keep practicing. Someday you might even be a pilot and fly a real airplane. Okay?
Yeah.
Mr. Wizard's World will be back in less time than it takes to boil water.
One kid's meal right away. Can you make that too? Could you please pass the chicken? Certainly.
Now at Burger King, lickety splits.
May I have the French toast? My pleasure.
You can collect all four, a new one each week when you buy a kids meal.
Room for a little dessert?
The Burger King Kids Club, just for fun, just for you.
Here it is.
This fall,
America is watching ABC.
make way for an exciting superhero.
I am Darkwing Duck.
Crime fighting has never been this much fun.
Let's get dangerous.
It's Darkwing Duck. Then, if you dare, there's adventure out there. In a world where dinosaurs rule. Enter the land of the lost. This fall on ABC.
It's the Handy Snacks Awesome Toy Giveaway.
The fun part.
You could win a $100 or $500 gift certificate, good for anything at Toys R Us.
Wow. The boring part.
You can look in specially marked Handy Snacks 8-packs.
More fun.
Thousands will play, hundreds will win.
More boring.
Or for free game piece and rules, write Handy Snacks Box 4612 Blair, Nebraska 68009.
Fun. Boring.
No purchase necessary, void where prohibited, subject to rules. Game ends 4/30/92.
You're watching Nickelodeon. And now back to Mr. Wizard's World.
Have you got a microscope, Kristen?
No.
Well, lots of kids would like them, but they're kind of expensive, aren't they?
Yes.
And yet I sent you over to my friend Bud Wentz, and he showed you how to make one. And what did you need? The most important ingredient?
Water.
Yes, drop of water. Well, I've collected everything that you need, and the important thing here is if you have a piece of plastic like that, come in a refrigerator jar, and you put a drop of water on it, watch what happens.
It just magnified all the words.
Yes, it magnifies all the letters. In fact, you can pick it up and make it magnify even more.
Yeah.
Okay, now, the big important question is why?
I don't know.
Well, a glass magnifier is sort of a rounded surface on it, isn't it?
Yeah.
And the light, when it's reflected through there, is bent in such a way so that magnifies things.
Oh,
so that's what you've got here in the drop of water.
I get
It's
it.
a transparent material with a rounded surface so it'll bend the light the right way.
I get it.
Well, that's a simple magnifier, but Bud showed you how to make a real microscope. And I think I've collected everything you need, so start from the beginning. What do you do?
Okay, you need a jar with a wide mouth here, and you need the jar lid with a little piece of plastic in, which came from
Right, I took it off of that, right.
And then you tape it on, and you put a little wee hole inside the...
It's inside the lid there, and you put the plastic over the top.
So you can see a little hole through the glass.
Okay.
Then you have just foil on a piece of cardboard there.
And why is it sitting on that piece of paper? So you can turn it, right?
Yeah, okay.
Okay.
I see.
So then what?
Then you put the jar on top here, and then you turn it to see where the light is, and then it would reflect it and come through the glass.
The light's hitting that aluminum foil and bouncing up to your eye. Okay.
There, I got it.
Okay.
And then you put whatever you're going to magnify. We're going to do salt, right?
Okay, salt's good.
Okay, and then put a little wee bit, not too much. And then you got to make sure it's spread it around so that you can see.
Because you want to see around each grain, right?
And then
Next.
you have that, and then you put a tiny little drop of water on the surface where the
Right over
little
the hole. Okay.
But you got to make sure it's right over the hole.
You want to use a medicine dropper?
Okay, sure. So.
Because I also have toothpicks over here. They work too if you don't have a medicine dropper, right?
Well, let's try the toothpicks.
Okay, you want to try toothpicks? Right. Now, what are you trying to do here?
Okay, you need to get a little drop on the toothpick.
Now, why are you trying to be so precise? What is it that you're trying to accomplish here?
Well, we want to get it right over the center so that we can see a better...
And also, you want a very small drop, don't you?
Right.
Because the smaller the drop, the more curvature, and therefore the higher the magnification.
You're right. Right over the center. There.
Okay.
I got it.
Now what do you do?
Now, you put this over the top, and you look directly through, and you can lift it up a little bit to focus.
Okay.
Focus in on the salt.
On the salt.
See if I can find some here. There. And then you can easily just take a look at it.
Yeah, great. So that means you could put all kinds of things in there on top of the bottom of the jar, which is now the top, and look at it with your little microscope. Now, how much did you magnify? Have any idea?
No idea.
Well, come on over here. I have the same salt set up here with my special equipment. Here's the salt sitting on I have it scotch taped to the front of a piece of glass, and it's being reflected over here to the lens, through the television camera, and finally up here to my little monitor.
Wow.
Is that about what the salt looked like?
It looks just like it.
Yeah. You said little, what, cubes or squares? They're actually cubes. Okay. Now, let's see how much magnification that is. I'll take this down. Here's my little television setup here, my little monitor. What's the width of the screen? What does it measure?
15 centimeters.
150 millimeters.
Oh, yes, 150 millimeters.
Okay, 15 centimeters, 150 millimeters. Now I'll put a scale here with my microscopes or sort of really long lens setup, and there are millimeters again.
Oh, I see.
Okay, how many have you got?
Got 1, 2, 3, 4, 5, 6, 7.
7. Okay, if we take 7 millimeters and magnify it so now it takes a space of 150 millimeters, how much are we magnifying?
Oh, okay, let's see. Around 20?
Yeah, 20 times. That's a fairly easy magnification to achieve with the water drop microscope. And if you make a real tiny drop and get everything working right, you can get up to 40 times. So you really have quite a bit of magnification. Well, because you and I both can't look through the water drop microscope, I've collected a bunch of stuff to look at this magnification of 20 times. You recognize that?
That's bicycle reflector.
Bicycle reflector. And if you take a look at it magnified 20 times, look what you see.
Look at that.
Yeah.
Wow, I never knew it looked like that inside.
Well, the reason it looks like that is that the scientists who discovered this principle and made these kind of reflectors realized that when light goes into it, it bounces around inside all those little prisms and comes right back out at the same angle that it went in. And that's why you notice when a car light hits it, it really shines. And that's the reason, because it's made up of those little six-sided prisms. Now, you probably have never looked at one of the most common things, and that's a watch. Take a look at a watch magnified 20 times. Okay. And of course, if it's an open kind of watch, you could see all kinds of things. But the thing that I wanted you to see was what happens to the minute hand. There's the minute hand. See, here's the hour hand up here, okay? Here's the minute hand. Now, when magnified 20 times, you're also magnifying the movement of the minute hand.
You can see it move a little.
Yes, you can actually see the minute hand move when you because you're magnifying the movement by the same factor as you are the size.
Wow.
Then one of the most interesting things to look at, you can go to any pet shop or aquarium shop and get brine shrimp. And they're little tiny things that aquarium people feed to their fish. And you just put their eggs in water, salt water, and let them sit for 24, 36 hours or so. And you now can look at real live animals. There they are.
Look at them. And when you look at them from here, they're so small.
Yes.
Now you can see everything.
They're the eggs in the bottom, see?
Wow.
If you watch them, you can even see some of them being born. So this is a nice thing to look under your water drop microscope, because you can put a little pile of water there and put the little brine shrimp down, get down your water drop lens, and observe them. So you did very well with the microscope. Good luck with yours. You can make one now anytime you want, can't you?
Yep.
Hi, Mr. Wizard.
Hi, Michael.
What are you doing?
Well, come on over here. I'll show you.
Okay. Well, what is it?
Well, I could tell how fast you were going without even looking at your speedometer. That ought to give you a clue as to what it is.
Well, it looks like a radar detector.
Not a detector. This is the gun in which they check to see how fast you were going.
Oh.
You've seen one of these, haven't you?
Yeah, well, my dad got caught speeding one time, and I looked in the police car, and there was one of those on the dashboard.
Yeah, you're right. You know how it works?
Well, I guess that when a car goes by or something, like it goes through this, and then goes through the cords and everything, and it comes out as a reading on a computer or something.
It's sort of like a black box.
Yeah.
Well, actually, as a matter of fact, it's sending out invisible waves, and they bounce off of whatever it is and come back here, and now it checks the speed with which the waves come back and makes the calculations, and you read it out here. You were going about 10 miles an hour. Here, I should check you on it because I want you to be able to use it later. All you do is point it at where you want to shoot, or whatever you're going to check. Squeeze the trigger, and it'll give it back here. Okay. Now I'll ride your bike, okay? Can I do that?
Sure.
Get me, Michael?
Yes.
How'd I do?
Did good. You did about 13 miles per hour.
Okay. Well, now that you know how it works, why don't we see how fast you can really go? How fast have you gone on your bike?
Well, I've got about 20 miles per hour one time.
Okay. Why don't you see how fast you can go, and I'll check it with this.
So how did I do?
Well, pretty good. 21 miles an hour.
Oh, wow.
Yeah. Well, now that you know how to do it, you could go out and check cars and that kind of stuff.
Way,
but let's do some stuff that's a little more interesting.
Okay.
In fact, you've probably been there before.
Where's this at?
You'll see.
Okay.
Okay. So what'd you get, Mike?
Well, it says here 17.
Was it the same all the time?
No, it wasn't. It varied.
When was it fast? When was it slow?
It was faster when it came down, and then when I pointed it to the front of the boat, and it was slower when when it passed by.
It was going about what, 18 miles an hour as fastest?
Yeah.
Okay, let's try the next one.
Okay.
Okay, you've been on this roller coaster, haven't you, Michael?
Yes, I have.
What's the fastest part?
Well, it's at the bottom of the steep hill.
How fast do you think you were going?
Well, it felt like I was going about 100 miles per hour.
Okay, stand by with a radar gun because the guy is about to turn the corner. Getting ready for the top of the steep hill. Radar beams are going out, bounce against the car and back. And are you ready?
There you go.
There you go. You thought you were going 100 miles an hour at that point?
Yeah.
How fast were you going?
I was only going 34.
34.
Well, it seemed like I was going faster when I was on it.
But I'd trust the radar gun, wouldn't
Yeah.
you? Okay, good.
It's more accurate.